Okay, good afternoon. Before I start the lecture, I have two announcements. First of all, there won't be any office hours for the rest of the semester, which is basically this week and next week. If you guys want to meet, send me an email and we'll schedule a meeting. Second, quiz 10, which is the last quiz, will be released this week, but not today. So I'll wait until Friday so that you're done with your lab, and then we'll release it on Friday after the class, and the deadline will be on Monday. And I guess the third announcement is that the lab is due on Friday, so make sure to submit your projects and also your peer reviews. We have we ran MOS on past labs, and fortunately there was no flags raised, so that was pretty much a good news for everyone. So we'll be running MOS on lab 4 and 5 as well. Okay, so let me get started with the lecture. Okay. Okay, so we were talking about flash memory, and we sort of talked about the structure of each NAND cell that pretty much mirrors what you have in a usual transistor, with the exception that here you have a negative, a floating gate that could be negatively charged. And the way to read your NAND cells is to just apply a threshold, a reference voltage to the control gate, and see if you get you can read some current draw from the source to the destination, and if so, then there is nothing on your floating gate, meaning that you have a stored 0 on that NAND cell, and if nothing happens, there is no current, then that means that the floating gate is negatively charged, which basically means that, sorry, so if there is no current, that means that you have stored 1, and if there is a current, that means that you have 1, and if there is no current with the reference voltage, that means that you have negative charge, and you have stored 0. So in hard disks, in magnetic disks, the unit of addressable data, we called it sector, and it was something around 512 bytes each sector, a usual size for a sector. When you're talking about SSDs and flash memories, usually the unit is called page. So we're going to use a physical page, at the same term that we used for physical memory. So the unit is basically a page, and the size of a page is is varying across different technologies and different flash disks. It's somewhere between 4 kilobyte to 16 kilobyte. Now you can read data with this granularity. You can also write data to a page. The difficulty is that when you write data, you first need to erase your flash cell. So to give you an idea, let's say your flash cell currently is storing 0. That means that you have negative charge on your flash. So you first need to remove everything from your from this floating gate. Remove this charge so that this cell is ready to be written to. So before we even start writing to our flash, we need to erase the cells that we want to write to. The problem is, unfortunately, you cannot erase a page by itself. You have to erase bunch of pages altogether, and that's a physical limitation of flash disks and NAND cells. And the size of what we call block, which is basically bunch of pages, is much more than a single page. So you have bunch of pages together constructing a block that has to be erased all together before each one of them can be written to. And that creates some difficulties, which we will talk about. Good news is that you don't have any moving parts. So this eliminates seek time and rotation delays. You also have very low power and lightweight devices and drives compared to hard disk drives, which would consume a lot of power because of all those physical moving parts. And also, if you have had one of those, they actually are very heavy because of all the, all the disks and heads and all the moving parts. Okay. So let's start with reading from a flash memory. This is the easiest one. It's basically very similar to how you read from your physical memory. You basically have a buffer that your requests come, and then your flash memory controller dequeues from this buffer and goes to the page that corresponds to the address for these requests, and then reads that page and sends the data back to the processor. The transfer rate is usually limited, as always, by the controller and the bus. So this is nothing new. We saw that previously as well. So if you have a really fast bus connecting your flash memory to your processor, then probably the bottleneck becomes your controller. If you have a fast controller but not a fast bus, then the bus becomes the bottleneck. Yeah, so assuming that your controller can keep up with SATA bus, then if you want to read one page, a 4 kilobyte page, then SATA gives you somewhere between 300 to 600 megabyte per second. So effectively reading one page off of your flash memory would take about 10 microseconds. And if you want to write out the latency, basically here you have as before the queuing time, the controller time, and the transfer time. So here we have eliminated, basically, when it comes to the device, we have eliminated the seek time and the rotation time that we had to deal with the magnetic disks. And for your flash disks, for your SSDs, it doesn't really matter if you're reading sequential data or if you're reading random reads, because there is no moving part that has to seek to a certain track. So all of the NAND pages are accessible within the same address bus. Now let's look at the more challenging part of using an SSD device, which is basically writing to it. Now, writing is a little bit challenging, as I mentioned. First of all, let's assume that you have a clean and erased cell, and now you want to write 0 to it. So when I say erased, it means that it has no charges, which means that it's storing 1. Now, if you want to store 0, you have to put some negative charge on the floating gate. And to do so, it requires you to apply a lot of voltage to your control gate so that you can bring some negative charge on the floating gate. So this actually damages the cell as you do it again and again and again. As a result, each cell has a limited life cycle, and there are a certain number of writes that you can do to a cell, after which your cell cannot reliably be written to. So that's one important thing to keep in mind. So right off the bat, writing into your cell is a challenging thing, and each cell has a life cycle, how many times you can write to it. So this limitation has to be dealt with. So there are two things that we have to do with this limitation. The first one is that we definitely need some error correction code when your cell is close to its life cycle and it's in a gray area where you're not sure if it is storing the exact same thing. If you have error correction code, then you can deal with small defects in each page. So that's the first thing we need to do. The second thing that we have to do, we have to perform ware leveling, which basically means that we have to intelligently write to each cell, all the way up to its limit. We shouldn't overwrite the same cell again and again and again and again, because it will just burn out. To do so, we need to load balance. We need to have a way to write to all the cells. Instead of, let's say you have a hotspot, there is like this file that every application is using and they're updating it. So if you always write the data to that for that file to the same page in your flash disk, you will burn that cell, that page. So what you have to do is to load balance. And if you want to load balance, you need some level of redirection. So your flash disk has to, because your flash disk is the one that is aware of how many times each cell has been written to. So usually we'll talk about it. Your flash disk has to move pages around. So offer some logical page number to the file system, but then underneath, try to load balance all your writes to all the pages so that you don't burn each individual cell. So this picture actually puts everything into perspective. When you want to write, you usually want to write like a single page, a 4 kilobyte page, but then this write has to be written to a clean and erased page. The other limitation that you have, other than the life cycle of your page, is that if you want to clean a single page, you cannot clean a single page. You have to clean a bunch of pages, basically a set of pages that would construct a block. So you have to basically clean them all before being able to write to each one of them. Now that also creates some limitation. So that's where the flash device has to include a flash translation layer. This is the level of indirection I was talking about. So basically this layer maps logical flash pages to physical pages. And its main task is ware leveling. And doing so means that you have to make sure that you're not writing to each page more than its limited number of time, and you have to load balance. Now, let's say that you want to do this, you want to do ware leveling. Actually, let's talk about ware leveling later. Let me say one more thing that the flash translation layer has to do, and that is basically sector sparing. I talked about this in the context of hard disk drives as well, magnetic disks, where you basically keep a portion, a fraction of your capacity as a spare sectors, so that if you have bad sectors, you can use those. The same happens here. The flash memory usually has a fraction of its capacity preserved for sector sparing. In this case, page sparing, and it actually helps with two things. One of them is that if you actually wear out one cell, then you have a spare cells that you can use. The other thing that sector sparing helps with is, let's say you have used your entire capacity, or you're very close to your capacity, and now you want to write to a page. Now, in order for you to write to a page, as I said, you rewrite the page, let's say, you need to erase it first. But if you want to erase like one page, you have to erase the entire block. Now, in this scenario, if you have to basically read the entire block first, store it somewhere else, remove it, and then write them back. Now, to do this, if you're full capacity, you don't have any more capacity. But if you have these spare pages, you can use them to perform writes, even after you're pretty much utilized in terms of your capacity. So these spare pages have, as I mentioned, have two purposes here. Now let's talk a little bit about ware leveling and the process of rewriting a page. So let's say you want to rewrite a page. Intuitive way, or maybe a naive way of doing it, is, as I mentioned before, you read all the blocks, you erased all the blocks, all the pages in the block, sorry. So you read all the pages in the block. Let's say you want to only rewrite one page in the entire block. You basically have to erase the entire block. So you read them all, you erase it, and then you write them all back. So this is a naive and like a simple way of doing it. But as you can see, this is too much to do. So for each page that you want to write, you're basically writing the entire block, and that's not effective and efficient. So another way you can do it, because you have this flash translation layer, you can mark the old version as invalid. So wherever the data is stored, you basically assume that page is invalid now. You find an empty page. Hopefully there are already erased pages, and you write the new version to the already erased page. And inside your FLT, you redirect that virtual flash page to this new physical page. And all of this will be masked from the file system. So file system is just using those virtual flash pages, but then the physical layer here is doing the translations. And once you get to a situation where most of the pages in one block are invalid, then you can garbage collect. So you can, now that most of the pages are not, are invalid, you can now read a few live pages in that block and then erase the entire block and write those live pages somewhere else. Again, do the remapping. So that's where you have the garbage collection coming into picture. The only difficulty with this is that you somehow need to know which pages are alive, still used. So a bunch of pages that you yourself as the controller remapped, those But then there might be some other pages that were previously used by a file, but that file has been deleted. So from the file system's point of view, file system doesn't need to necessarily tell the disk that those pages are not used anymore. And that's indeed the case when you use magnetic disks. So if you delete a file, your file system doesn't go and tell the disk that this file has been deleted, because there is no point. Whenever you want to, write somewhere something, you could basically just rewrite to those sectors again from the file system's point of view. But with Flash, because it does the garbage collection, it's very helpful if the file system tells the flash disk that some pages are not being used anymore. That helps with the process of garbage collection. And that's where you have this trim command. So this is a command that was introduced specifically for flash disks. So file systems once in a while, like repeatedly, report to the flash disk, all flash drive, all the pages that are not being used anymore. So here is just an example of everything that I talked so far. So this is basically putting everything together. Let's say that you have here in this figure, I'm assuming that you have 2 free blocks, all erased. Now let's say that you initially write 4 pages. It goes through without any difficulty because you have 3 pages. So you write them down. Let's say in the next next IO operations, you want to rewrite all 4 of them. So now you have A prime, B prime, C prime, and D prime. And you also have 4 new pages to write, E, F, G, and H. So what happens is that your controller will mark these ones as old or not used anymore. So they become invalid. E, F, G, and H are being written. And instead of rewriting these guys, because you can't rewrite on top of the old ones, you have to write them in 3 pages. So we write them somewhere else, and the controller will remap those logical page numbers to these new physical page numbers. Now, at some point, you could do garbage collection. What you could do in order to free all these cells that are not being used, at some point, anytime that you have free cycles, spare cycles, you can basically read the entire live pages here, write them to another free block, and then garbage collect the old block. So that's basically what happens. So one point here is that as you can see, you basically wanted to just write, in this case, like 8 pages, right, in this second one, but you ended up doing some garbage collection, some other writes and reads and stuff. So it basically, what you have is write amplification, both because of ware leveling and because of the physical limitation that you have to erase all the pages in the block to write only one of them. What happens is that usually after you write your page will be moved inside your flash for garbage collections, for ware leveling, as you update your page. So in essence, each single write on average amplifies to more than one write. And that's one of the downsides of flash disks, because as we saw, you also have this limitation of life cycle, and you basically want to have this write amplification as low as possible, but it has to happen because of all the limitations that your flash NANDs have. Okay. So again, this write amplification shortens the life cycle of your SSD. It also consumes bandwidth, as you might imagine. So you usually want to do it when your flash disk is not used by the processor. So to do the garbage collection and all of that, because you're basically reading and writing, and you don't want this to interfere with the application that is using your hard disk. Sorry, your SSD. Now, if you put all of this together, if I ask you what's the performance of your flash disk, it would really depend on your workload and how your workload uses the flash disk. And that would basically, if you have, for instance, a workload that updates data a lot, so you might actually end up having lower performance than a workload that just writes or just reads. So it's really workload dependent what performance you get out of your flash disk. If you want to formulate your latency, again, you have your queuing time, you have your controller time. Here, control time includes finding a free block. And then you have your transfer time. Excuse me. Now, one thing that I haven't mentioned here, it might actually be worth mentioning. Here, usually erasing the entire block, which is called erasure, it actually might take a lot of time, right? To read them all, write them somewhere else, and erase the entire block. By remapping, basically what we did here is we first remapped A, B, C, and D to these new blocks. You could amortize the cost of erasing a block to all the writes that you have. So you could imagine, let's say, a scenario where you have the entire block written, and now you want to override every single page in that block. What you could do is to start writing them to another block and then mark them all as invalid, and then garbage collect the entire thing. So each write will just go ahead and write in a free page, but after you write the entire block, all of them are invalid. Now you can garbage collect. And then the cost of garbage collection basically amortizes over all those writes that you had. So that's another thing to to keep in mind. So that's another benefit of having this this level of indirection. Okay, so this is a yeah, probably I should change this current SSD. This was, I think, last year when I was looking at this. Things have changed definitely. So this is, as I mentioned last lecture, this is an area where it's evolving very fast. Like, let's look at some of the numbers here. The capacity, the maximum capacity at that point for this particular one was 2 terabyte. I'm 100% sure because of the cluster I'm in the process of buying myself. I know that this has increased to 4, 8, whatever. Now there are actually much bigger flash disks that you can buy. So that's that. Yeah, let's see what else here we have. So yeah, as you can see, the read bandwidth is higher than write bandwidth, which makes sense because of the problems that you have with write. What else can we see here? Yeah, so that's basically all the important things. Now you can go ahead and compare these numbers with the numbers that we got from magnetic drives, and these numbers are much higher than what you get from your hard disk. Usually orders of magnitude faster when it comes to reads and writes. I'm going to just show you the comparison with yeah, so to compare here, the maximum transfer rate was 261 megabyte per second. Compare that to 3,500 megabyte per second, which is pretty significant. Okay. So I'm actually going to move on from this slide. Definitely take a look at it. There was a New York Times article, 2011, which was very interesting. So because when you start writing to your flash, you actually put more charge into the floating gate. This means that as your flash drive becomes more and more used in terms of capacity, it should become heavier because you're storing negative charge, and negative charge has a weight. So there was this very interesting study that showed just on paper how much more weight it could get as you store more and more data on your flash disk. Okay, so what are the advantages of SSDs over magnetic disks? They have lower latency and higher throughput. They don't have moving parts. They're lighter, low power, a lot more silent than your HDDs. What are some of the disadvantages that again are changing? Expensive, a little bit more expensive. The gap is closing. In fact, you don't have the same performance for writes than compared to reads. That's basically kind of like annoying. that your writes are different than your reads, but that's what it is. And then you have actually limited life cycle for your NAND cells. And this is like a comparison between access time of an SSD and a hard disk drive. Power, energy savings, reliability is an issue. Higher random I/O performance, much higher than HDDs. And because of the speed, basically backing them up is also faster. Okay, so we're done with this lecture. Let's move on to the next one. Okay, so next we're going to talk about file systems. In this lecture, we're going to see definitions of files and directories, and then we're going to see 3 different file system implementations. And at the end, we're going to talk about, again, caches. So we're going to talk about buffer caches, how to make working with files faster. Okay, so what is actually a file system? File system is another OS abstraction. What is the purpose of file system? It has 2 purposes. One, we want to provide persistent files, persistent data. So if you write to a file, we want this file to stay available until you explicitly delete it. We also want to address our files in a human readable manner. So we're going to assign human readable identifiers to our files, and it would be the job of the file system to translate those files, those human readable identifiers, to actual data blocks on the storage medium. So to just list some of the things that the interface has to do for us, we wanted to provide naming, as I mentioned. It has, in some cases, it has to be optimized for the storage medium that it's managing. So if many file systems have optimizations for magnetic disk drives to make it faster to read and write to them. So you want some sort of, data storage management. You wanted to provide protection, keeping the data isolated and secure, the same way we did with memory. And we also want reliability and durability, which we'll talk about in the next lecture. So we'll just set the scene for why these are important, and then hopefully talk about reliability and durability in the next lecture. Okay, let's start with files. What are the files? What is a file? File basically is a named set of blocks in file system. That's in essence what it is. Now, usually files are used to store data. That's basically what their purpose is. What data do you have in a file? The first one is your actual data that is associated with the writes that happened by your program. So this is basically the information that the user or the program created and gave it a name. In addition to your actual data, usually your file system and the operating system also wants to store some information about that data and about that file. we call that metadata. So basically, who's the owner of this file? What's the size of this file? When was it modified last time? What are the permissions for the owner? What is the permission for anybody else? And so on and so forth. So that we call metadata. Now, from the user's point of view, the data is the file is basically a durable, it's a durable data structure. So it has to be durable, it has to be persistent. From systems point of view, to provide that to our users, we need to do a lot of things. So when the system looks at files and data that is stored on the storage, depending on which part of the operating system is looking at the data, they might have different perspective about the data. So when user stored its data, maybe they stored a linked list in a file, or maybe they stored a picture, a file, a MPG file, or maybe it is a movie, right? These are frames of a movie that are stored in this data. So there is a data structure that from the user's point of view, it's durable, and then there is a program that can read this file and work with the file. Now, coming down to the system, if we're at the system call interface layer, we usually don't care what is inside the file, what data structure the file has. We usually care about bytes. So we're just looking at a file as an array of untyped bytes, basically characters. We don't really care about what is in it. All we need to do is to be able to read and write from that file, and provide system calls to the user to do so, to read and write from that file. Sometimes, though, that being said, sometimes the operating systems provide some look at files given their structure. So one example is if you're in Linux, if you have a.out, if you have compiled your code and made an executable file, then if you double click on that file, your Linux operating system starts executing it. Somehow it knows that that file, and it starts running it. So there are examples of it in all operating systems, Mac, Windows. So those are basically kind of like utility functionalities that the operating system is providing. But it's more specifically from the users, from the systems call interface point of view, you're just dealing with a bunch of untyped bytes. And now if you come down another layer and look at the file system itself, again, from that layer, I'm just looking at it as a collection of blocks. So a block is, as we will see, is usually like something about 4 kilobytes or more of data. It's actually more. I think it's if I'm not mistaken, yeah, something. I mean, it's you can definitely configure it. I don't want to say something and then regret it. So we'll talk about it later. But a block size is usually bigger than character size, and definitely, I mean, a character is basically 8 bytes. A sector size is 512. 512 bytes, and a block size is more than that. Sometimes, as I said, it's like 4 kilobyte. So from the file system's point of view, I'm just looking at a bunch of blocks, which usually are in kilobytes of size. Now, what are the file access patterns that we usually see? Sometimes we're accessing our files in a sequential manner. So let's say we want to read a file from byte 1 to byte to the end of the file. So you basically say, okay, give me the next byte, give me the next byte, give me the next byte. So you're sequentially reading a file and going through that file. You could also have random accesses, either reads or writes. You could say, go to the middle of the file and give me these like bytes from I to J. So that could happen. One example of that is, let's say, you know, you're for paging. Let's say you have a swap file, which contains all the pages for one process. So let's say you have evicted an entire process and all its physical pages to your disk, and now you want to run it again. So you could, now that you want to start running it, you could potentially say, give me these pages. So you go to that swap file and you say, read from here to give me this and that pages so that I can run my process. So this is one example. It's not that common, but it still could happen, right? These random accesses. And sometimes you might have content-based accesses. For instance, you could, you know, have, you could say, okay, give me bytes that start with this pattern in this file, right? Usually for this, the system call interface or the file system doesn't provide a specific functions, and you could write your own libraries to provide this, but sometimes you might actually include them inside the system call interface, or you might want to include them in your file system. Yeah, I think one example is the Mac OS Spotlight search. So that's basically very similar to this. You could, you know, search for a name and then show you all the files that start with this name and such. Okay, so now we want to go from user's view to system's view. So what happens when your user asks for a specific bytes? Let's say, give me byte 2 to byte 12. So as I mentioned, your file system looks at files in terms of blocks of data. Usually a block of data is, as I said, something like 4 kilobyte, right? So you're going to read an entire 4 kilobyte by your file system. And then from this 4 kilobyte that you read, you give your user byte 2 to byte 12. The same with writing byte 2 to byte 12. From your file system's point of view, everything is a block. So even if you change few bytes in a block, your file system is going to assume that the entire block has changed. So it's going to overwrite that block. So basically, the underlying message here is, although the system call interface provides ways for users to read and write just bytes, like get C, put C, under the hood, what we're doing, we're working with blocks, and we have to keep that in mind, because there might be optimizations that we might be able to do to take advantage of this and make things faster or more efficient. Now, before jumping into ways to implement file systems, as always, so if you remember the entire course, every time we wanted to talk about a new topic, we looked at trends. We need to know our audience. We need to know what are their needs. We also need to know what are the trends in, in the hardware. That's basically what we did with the previous lecture. We talked about what are the trends in persistent memory. So here is just a very light overview of what the users of our systems want to do. So first we saw that they usually want to work with bytes, and that's basically what our system call interface is providing. Now let's look at what are the type of files that our users usually have in the system. So this is a very interesting study from Microsoft Research. They looked at 5-year data usage of bunch of users, and this study actually gives us some important perspectives that would help us in designing our systems. So the first important takeaway from this paper was that most files in our systems are small files. So usually you have really small files, and the other trend is that the number of small files, not only they are the majority, but also the percentage or the fraction of small files in our systems is actually growing. So this is the graph. On the x-axis, you have the size of the file, and on the y-axis, you basically have the frequency, or basically the number of files per file system with that particular size. And then different curves here are different years. So they looked at files from 2000 to 2004. So as you can see, most of the files in the system are small files, like 2 kilobytes to 32 kilobytes. And as you can see, the variance is going down. So in 2004, we basically had a very low variance, meaning that there were a lot less fraction of data that was really small, like 8 to 128 bytes, or very big, like 512 kilobytes to 128 megabyte or even more. So most of our files, most of the files were small files. The other observation that this paper provided was that most of the disk space is occupied by rare big files. So although we don't have many big files, but 1 or 2 is enough to occupy most of our disk spaces, our disk space. So in this graph here, you can see the size of the file. And here on the y-axis, you can see how much of the capacity is used by those files. So for instance, and then again, the curves show different years. So just look at this one. So if let's say you look at files that are 2 megabyte of size. In 2000, they were occupying about 300 megabytes. So basically you had, if you divide on average, right? So this is 300 megabyte, and each file is 2 megabytes. So you basically had 150 of them. So you had 150 files on average, and in total, or on, yeah, again, so they would occupy something around 300 megabyte in your file system. This number actually increased. So as you can see, the peak is shifting from, not much though, but it's basically going up here, and you're getting another peak here. So you have one peak here around 2 megabyte to 16 megabyte. And then you have another peak here around 1 gigabyte. So this one is interesting, right? If you look at 1 gigabyte and let's say 2004, you can see a file with 1 megabyte on average occupies slightly lower than 1 gigabyte. This shouldn't be counterintuitive because this is average. That means that there is a probability of 95%, for instance, that a file system has a file that has the size of 1 gigabyte. So that's the average. So not every user had a 1 gigabyte file. That's why it's like 95. If you divide the capacity divided by size, you get like something around 0.95. That's basically the probability of a file system having a big file like that. But that's basically what is occupying a lot of space. Even if you have one of them, they occupy more capacity than all these little ones that you have. You probably have, if you divide these numbers, you probably have a lot of these thousands of these files. But even thousands of these files, that would put you, let's say 2,000, 3,000 of these files would put you in, let's say 600, 700 megabyte. But then if you have only one gigabyte file, you already have occupied 1 gigabyte size. And again, this also is moving. Probably if somebody does this study now, you probably either will see these peaks continue to be shifted towards bigger files, or you might actually see multiple peaks in this graph. It would be interesting if somebody does this study again. So putting it all together, we had two observations. One, most of our files are small. Second, large files actually use most of our storage space. And this shouldn't be counterintuitive because of the nature of this too. So what should we do with these with this information? First of all, this motivates us to kind of like focus on small files because we have a lot of them. So we have to sort of be really fast when we are working with small files. But we should be aware that those big files exist and they occupy a lot of space. So one thing that people have thought about is that maybe because of the way that the file systems behave, because all of them are, optimized for, smaller files, that has incentivized users to have a small files and not to have big files. Because if you have a big file in your system usually sucks at it. I myself have had this a lot of times. Like you're working with a VIM or Vim, you open a big text file, and all of a sudden your computer is just freezed. So maybe because of this, people tend to create and maintain smaller files. So this is a gray area, right? You first of all want to be good at the usual use cases, which basically when it comes to files means that you have to be good with small files. At the same time, you also don't want to screw it really bad with the rare cases. Okay, so that all being said, let's now look at how we can organize files and then how we can implement them. The first step is to organize files in directories. That's basically coming from being able to name our files in a human readable manner. If you want to, have a good sense of what directories are, they're usually, not always, basically a tree structure, a hierarchical structure, where you have folders that contain documents. Now, those documents could be, again, folders or individual files. So with that recursive definition, you basically get a hierarchy, a tree, representation of your files in your system. Again, I want to say it's not always tree, right? I'll probably talk a little bit more about that. Systems usually have a root directory. Think about this root directory. If you think about your file system as a tree, well, that tree has a root, and that root is basically your root directory. If you're in a Linux, a backslash is basically, I always mess it up. Is it a backslash or a slash? If somebody can use the Q&A. Anyways, so you can use this character to specify the root directory. And now, what is a path? So you have two types of path. One is absolute path. An absolute path gives you the path from the root directory to the file that you want. So in this case, the root directory, then home is another directory. From home directory, I go to SMZ directory, and then I find my file there. So this is an absolute path to my file. I can, if I'm actually currently in my home directory, then I can have a relative path to the file that I want. So a relative path would be from where I am right now, from home. So I could just say here, you just go to the SMZ directory, and then you can find your file in that directory. The other thing that usually file systems provide is that you can create links to files. And there are two types of links. One is hard link. The definition of hard link is basically creating another name or another path for a given file. So let's say you already had this path, this file, this foo file in this directory. So you had usr lib7 foo file here. You can create this other path. You can say usr lib foo also points to this file. So you gave this file another name. So it originally had usr lib7 foo name, now has another name, usr lib foo. Now, here comes the difference between hard and soft links, which I'll talk about later. But if I delete any of these two, the other one will work. Let's say I delete the original file. Let's say I delete usr lib7 foo. What happens is that that name is disassociated from this file. But because this file has another name, I haven't actually deleted the file. So I have only deleted one of the names for that file. Now, if I delete this name, I can be sure that I have actually deleted the file completely. Now, there is also another kind of link that file systems usually allow users to have, and that's called soft links. Sorry, I should have mentioned. So in Linux, for instance, in Linux systems, Unix-based systems, you can create a hard link by using ln application or ln command. So this would be the original name of your file, so path to the file, and then this would be the second name that you want to give that file. And this is how you can create it. Now with soft links, you just add a -s to say that this is a soft link. And the difference comes with how you can delete the file. So if let's say this usr lib foo file, this usr lib foo is the soft link that you created. If you delete this one, sorry, if you delete the original file, then the actual file will be deleted. So that's where the difference comes. With hard links, this wouldn't have been the case. But with soft links, now this link is a dangling link. It's not pointing to anything. Now, the same way that we looked at accessing files, you can look at accessing directories. Let's see, how much time do I have left? Okay. Okay, now we usually store directories as files. From the file system's point of view, a directory is another file. Now, what does that mean? That basically means that you can use the system calls like open, create, to access the same system calls that you used to access files. You could potentially use the same system calls to access directories. They probably will have permissions so that you cannot mess around them, right? You might not be able to write, for instance, to a directory because of the permissions. But you could read it. For instance, if you have vim or vim, you can open a directory and look at what is inside it in terms of what kind of data is stored in that file. But then there are specific system calls that are provided by the system call to work with directories. So you can make directory, you can remove directory, you can link files and directories, you can unlink them. So on top of the usual system calls that we have to work with files, we also have system calls to work with directories. Because of all the links and that you could have, usually when you delete a file, your file system kind of tracks how many names are associated with this file, how many hard names and actual names. And when there are no references to the file, then you could delete that file. Yeah, I'm gonna just actually move on from these. I'm pretty sure you worked with files a lot in ECE 252, so you should be pretty familiar how to work with files. What are the system calls available to read, write, and do all sorts of stuff with files. Now, another term that we have to define when it comes to file systems. So far we've seen files and directories. The next term is volume that you will hear when you read about file systems. So what is a volume? A volume is a set of drives, physical storage drives, that provide a unified logical storage device for the file system. Now, each instance of file system can work with a single volume. So again, you could potentially, have multiple magnetic devices, magnetic storage devices, to create one big volume and let your file system take care of the entire volume. Or you could install one file system per disk drive, and in that case you will have as many file systems as you have hard disk drives. The limitation here is that so the limitation is that you want one file system per logical storage or per volume. Now, you could mount a volume to an existing file system. This is another term that you probably will hear a lot when you're working with file systems. So if you mount a volume and its file system, let's say you have a volume with a file system and you have another volume with another file system, you can mount this new volume to your existing file system. And what that does is basically it maps a path in your existing file system to the root directory of the new volume and its file system. I think it would be easier to see it in a picture. So let's say this is your USB disk drive. So you have actually installed a file system on it, and it has let's say two folders and a file, a movies and a backup and only one file. So this is the root directory of your USB volume. Now, let's say you on your laptop, you also have a file system. And let's say this is a Unix system. You have volume, bin, home, and so on and so forth. You could create a folder here, name it USB1, and then mount this volume to this folder. This volume to this file system. And what that does is basically maps this name from root volume USB1. So this path will be mapped to the root of this second file system. So what happens if you want to access this file? Well, now the address of this file becomes root volume USB1 movies, and then your movie file. So what happens is that your original file system will parse the first 3 folders and then figures out that this is mapped to the second file system. So it excludes all of the prefix of that path. So it parses that one, and the remaining, it passes it to the file system that you have already on your USB volume, and let the file system deal with the rest of the address. You could now mount this on a different file system as well. So let's say now you have Bob's disk. Bob could also create a folder and mount this USB volume to that folder. Again, the original file system will find out that the address that you're using is mapped to the other file system. It passes the appropriate address to the secondary file system and let the secondary file system deal with the extensions of that path. Okay, so now we're at the point that we can start talking about implementing our file system, because now we know the building blocks of the file system, namely files, directories, and volumes. We know user access patterns, and now we are ready to implement what a file system has to do. So going back to the definition of file system, we need 2 properties. We need to be able to name our files. So we need to have a naming system. We also need persistency. We need to be able to store our files in a persistent manner. So let's start with the naming. I guess I only have 1 minute, so I probably can finish this slide. As I mentioned, a directory is basically another file. So if you have a path that you want to use to access your files, what you can do is, in a recursive manner, you can read each directory in your path to find the next part of your path. So all you need to do this recursive, to implement this recursive functionality, is to have file names and file numbers pairs. So all we need to do is to associate to each file name a file number, and then store these inside our directories. And again, this file name could be by itself a directory. So here is an example. Let's say we're in SMZ directory, and then we want to find foo.txt file. We can just read this directory, this SMZ directory. By itself, it's a file, so I can open it and I can look into its data. So hopefully what I will see there is that I'm looking for this foo.txt to find a file number for this file. So I can see that. In addition, I might actually have 2 other folders here. I might have this SE350 folder, or another directory, or ECE350 directory. So these 2 also have file numbers. So now if this path, instead of looking for foo.txt, if I was looking for home SMZ slash SE350 slash foo.txt, then I can now look at this SMZ, find 739, go now open that file and look at foo there. So this is putting it all into perspective. From the beginning, if I have a path, I can look at my root directory. So probably I need to have a specific file number for my root directory. Usually Unix systems keep number 2 as a predefined file number for the root directory. So there should be something that I should start my recursive search from. So again, in Unix systems, usually it's 2. So let's say I open file number 2 as my root directory. Now I look for /home. So now I see that home is file 119. So I now have this number. I can open that file. I can recursively now search for SMZ. Now SMZ has 110. I can now open file 110, which would be SMZ. And now I can look for foo.txt. I can see that this file is 158. So I actually find my file. So basically, this recursive procedure turns our human readable path or file name to a file number. Now, in the next lecture, we're going to talk about how we can find data blocks associated with this number. So in this one, I didn't specifically say how we opened each one of these. I assume that if I have a file number, I can open that file. In the next lecture, we will talk about exactly how this could happen. So if you have a file name, how can you find data blocks associated with this file number? So that would be the topic of the next lecture. Sorry, again, I went over time. I'm going to stop here. Thank you, everyone who attended the lecture today. We'll talk to you on Friday. Take care, be safe, and bye-bye.